Okay, thank you, Rainer. I will not waste some time to introduce myself. I hope everybody knows me. I'm the CiA Managing Director since 1992, when CiA was established. Just a brief history, and this is very short. It's just one slide, and Rainer has already explained this very nicely. So, as said, 40 years ago, then there was introduced the CAN protocol in February 1986. And since those days, there have been two additional protocol versions be released in the year 2016. The KNFD protocol, which was explained by several of of the other speakers, and then we have also the KNXL protocol. So all three protocols can be used to interconnect AI-based devices, of course. And we will see how this works. Before we go into that, we will also have a brief history of artificial intelligence. And you may know that artificial intelligence is based on the assumption that the process of human thought is performed, can be performed by means of electronic. Oh, what is now happening? I lost my. As you can still see my slides,
Yes, we can.
but I can't. Yeah. Okay, now I can. So by machines, and this idea is quite old, older than technology is, or electronic technology is. In Greek methodology, Talos was a creature made of boss who acted as a guardian of the island of Crete. And he would throw boulders on the ships of invaders. So this means also in those days, they were thinking that there is a machine which can decide by itself who is an enemy and who is not an enemy. The term artificial intelligence was introduced much later. This was in July and August 1956, when there was a workshop organized by these four gentlemen, which you see on the bottom. Artificial intelligence as the ability of machines or electronic machines to perform tasks that normally request human intelligence. Okay, now, such as learning, problem solving, and decision making. So this is what those artificial intelligence algorithms are doing. The core function of an AI system is they are designed to mimic human cognitive functions, like analyzing data, making predictions, and executing actions to achieve goals. Learning and adaptation, a key characteristic is the ability to learn from data and to improve performance. And this is in contrast to traditional programming, in which a system follows just pre-written instructions. So now you can improve yourself, or these kind of machines can improve themselves. And you know all these applications, and I think you are using them every day for recognizing images, understanding and responding to language, solving complex problems, automating customer support, making data-driven predictions, etc. This is a very broad technology. And the technology is not only a single one. You see, when I look to the internet and find all the artificial intelligent terms which are hanging around, then it starts from agentic AI, which makes autonomously decisions, up to the theory of mind AI, understanding emotions and intentions. And in between, there's a lot of other artificial intelligent terms. But we are interested only in a few of them. And I try to summarize them in the next slide. So this is regarding the location of the artificial intelligence processing. So there's a cloud AI, and the definition is this refers to services and resources that are hosted on cloud platforms such as Google Cloud AI or Amazon Web Services AI, etc. This is something what we are using every day. The edge AI, this is at the edge of the cloud or at the internet. This refers to the deployment of AI models and algorithms directly on local devices, such as edge servers, IoT sensors, or smartphones, rather than a centralized cloud service. By moving computation to the edge, data is processed at its source, enabling devices to think and make decisions in real time. Because if you have to trust the cloud services, this can take some time. There's also an embedded AI, and we should also define this. This is the integration of machine learning models and algorithms directly into hardware devices or specific software applications without any access to cloud AI systems. So this is the three-level approach, which I think we can look at, and then we will have some more understanding where can interfere with that. So Edge AI, this function runs on a powerful device located near the data source, such as a local server or a gateway that collects data, optionally CAN connected from traditional sensors controlling traditional actuators, optionally also CAN connected. And the scope is performs high-level analytics and decision-making by combining data from multiple embedded devices. The hardware, what we need is a little bit more powerful processor than typically for non-AI applications, but still keep the processing local instead of in the cloud. Example, as you have might be seen in some hospitals already, there are gateways that analyzes data from multiple patient monitors to trigger an alert for a critical condition. And of course, they have a cloud connection, but this is not necessary to perform the analysis and the warning to the nurses and the doctors. The embedded AI runs on a sensor or actuator equipped with an AI-capable function, embedded in a single device, optionally, of course, CAN connected. The scope, the AI's function is limited to the task of that specific device. So it's very dedicated functionality, and such as signal filtering or anomaly detection within the device's own data. Hardware, of course, it needs very specialized AI-capable processors, and they should be completed by AI software. Example, a sensor fusion device with built-in item recognition that can identify an object on its own. You don't, if you implement this, for example, in agriculture machinery, we will see later on some examples, then you don't want to have, or you need an access to the cloud AI, because this should be done directly on the vehicle. So, but there are some synergies, and this was what somebody from Fraunhofer told me. This is not a clear border between edge and embedded AI. Sometimes you have the same functionality in one device. So this is more a theoretical distinguish between edge and embedded AI. So they work together in a hierarchical system. Embedded AI handles the initial on-device processing into intelligent pre-filtering data. So an edge AI that takes this AI process data from multiple CAN-connected embedded AI devices for a more comprehensive analysis and decision. We will see some examples later. This approach minimizes the amount of data sent via the CAN network, which saves bandwidth and improves response time, enabling even hard real-time control tasks. So you can regard this in a picture. You have the cloud AI, they have the edge AI, a host controller, and you have the simple embedded AI devices connected via CAN to the edge controller. And then you can see how that works together, all even without a cloud AI connection. And the benefit is that these low-end devices, they don't need a lot of energy, because you know that cloud AI is really energy eating and requires a lot of performance on or consumption of energy. And this trend to decentralization of AI, this is normal, because if you have a centralization, and this is an organizational structure in which decision-making power is concentrated at the top, and the decentralization distributes this power across different levels. And this is something what happens right now. And if you have been on the Embedded World exhibition, you have seen a lot of hardware and software just supporting this decentralization. It's not only embedded AI, there's physical AI. And you see this on the picture, the difference. In physical AI, the device itself has directly access to the physics by means of the sensor. This is typically done when you have a sensor fusion device. If you have traditional sensors, then you can collect the data from the sensors via the K network, and then you have an embedded AI entity which then runs the AI algorithms and models. So these are two implementation options which you have, and you see that both can use K networks for that purpose to communicate with other devices. So physical AI definition is not only related to sensors, it could be also related to actuators when you have physical access for motion and those things. For example, if this is a robot, a car, or a drone, and this allows to manipulate the environment. And the embedded AI, this is more that you have the head, so to say. Then you collect from others some data, and then you process this with your AI algorithms. And so the focus is here more running interference directly on hardware with limited computational power, memory, and energy, in particular energy. And this has also some benefits. So in those embedded AI, you have no access to the cloud. And this means you don't have to take too much effort on security because you are locally capsulated with your AI functionality. This is different than to the cloud AI. So let's look to some examples. Here you see a physical artificial intelligence application. This comes from the agriculture industry. This is one smart spray. This is a AI-based weed detection and destroying with lasers. So we have a camera, and the actuator is the laser, and both have some intelligence. And there's an embedded controller taking the data from the sensors and then destroying the not intended weeds. This was done for a dedicated company, was a joint research project by Bosch and BASF. A similar approach was also introduced. This is an AI-based spot spraying for sugar beets. And you see here also a lot of cameras and sprays. And this was controlled by a Fusion AI control unit from TT Control. And this is powered by the Hilo embedded software from this company. And also this shows that this is not only one company, this is already practically in use. The prototypes are already running on the fields and on the farms. Another application coming from the construction machines, you see here, this is a visionary AI assist, AI-based sensor system with J9039 interface. This is already existing and can be mounted on self-moving machines and the construction machines, also, of course, on agriculture machines or other mobile machinery. A similar thing has been developed by the company Turk. You see here also such a device which can detect that there is a bicycle in the field, and then you can stop your machine not to destroy the machine. Or if this is a human being, of course, then you also will stop. And note, the CiA 454 item detection profile supports sensor fusion and embedded AI functionality by means of dedicated quality of service information. What we need to do is for all those AI-powered sensors and actuators, we need to provide an additional information about the measured data or the calculated data. And we need to have a dedicated quality of service information. How good is the artificial intelligence process? This should be given with the data so that others then can decide how to react. Of course, if you're looking to military applications, you see there's a lot of more applications already on the market, and we can discuss this that there are drones which have no GPS signal and have no remote communication anymore, and then the necessary sensors are connected by redundant K networks to the AI-powered navigation controller, and those AI-powered unmanned aerial vehicles. For example, you see here two of them. They can identify and lock onto targets without human intervention. They are also called kamikaze drones, suicide drones, or killer drones. But this kind of application raises some discussion because this has some ethical concerns, because it's difficult to assign the responsibility for potential war crimes if you give anything to the machine to kill people. That is not theory. If you went, when I went to the Embedded World exhibition, I saw a lot of software. You see here, for example, NXP has some machine learning software which can be used on the very small microcontrollers like an ARM Cortex M0, which features optionally CAN Classic or CAN-FD connectivity. And this is suitable for image AI processing, for example. And this can detect for some plants and what kind of plant it is. And there's also an open source TinyML software, which is optimized for embedded AI and physical AI applications. But there are also more powerful hardware available. Rome has introduced some microcontrollers implementing a dedicated AI processor with a 3-layer neural network algorithm, and these chips come with CAN-FD on chip. And there are also special purpose controllers implementing the micro NPU from ARM, the U55 and U65 processors, and they are suitable for edge AI, embedded AI, physical AI, or some also call it endpoint AI. So we have not decided yet what term is we are like to use, but this needs to be harmonized. Otherwise, we will talk about the same things with different words. And such products are available from Aleph, CiA, Infineon, Nuvodron, NXP, Renesas, STM, and there might be more. And a lot of them feature CAN Classic, CAN-FD, and the first one, CAN, has already introduced that they will support CAN XL protocol controllers on chip of these special purpose microcontrollers. So CiA is also looking beyond its own membership. So we have some discussions with the non-profit AI Architecture Group, which is situated in Germany, in Munich. And we have started to negotiate cooperations regarding K-network AI devices in construction machinery, because this is their business. And this includes in particular preemptive, predictive maintenance and condition monitoring. And we negotiate if there will be possible joint project and that we can have prototype developments or feasibility studies and doing this together. And if you're interested in that, please contact me so that we can have a joint meeting with them and a joint workshop to negotiate what kind of cooperations we can establish. So the summary, AI is not AI. There are many shades of AI. Can connectable devices with embedded AI or physical AI capability provide hard real-time performance for deeply embedded control devices? Embedded AI and physical AI devices unburden the cloud-based AI with edge AI capability. Embedded AI and physical AI devices reduce bandwidth requirements compared with cloud-based AI, because the intelligence is then at the front end or at the endpoint. And existing CIA profiles can be reused or might only be insignificantly enhanced. And suitable MCUs with embedded AI and physical AI functionality are already available. So we can start right now. And we invite all participants or interested parties to contact CIA to make some progress in this direction. So, and embedded AI devices, from my understanding, is the next logical step of AI decentralization, which is needed for different reasons, to save power consumption, to improve real-time capability of control mechanisms powered by artificial intelligence. And democratic artificial intelligence thinking needs plurality. This means keeping technology compliant with democracy requires AI diversity by means of decentralization. We need a lot of different solutions, and not only one solution will be the correct one. This is like with human thinking. There's not only one opinion, there are many opinions, and and all of them are valuable. So this means we have a lot of different greens, not only the CIA green, so that we have a lot of greens, and also we should cover all those people, how they think, and this should be reflected in our AI-powered devices at the end. Thank you for your attention. And are there questions? No questions at all?
I don't see something in the chat.
You don't see something in the chat, so then I will stop presentation and go to my next presentation. You see already something? Yeah.
Yes.
So this is a more boring stuff. This is not looking into the future. It's also looking into the future, but not in the far future, but more to what is ongoing right now in international and national standardization, and what is in revision or in preparation. You have heard about a lot of CIA specifications, but this is not the only one who is releasing and developing CAN-related documents. There are also others are doing this, and we try to cooperate and to work with them. So just as a preamble, CIA commitments. So CIA was willing to submit any of its specification for international standardization to ISO, IEC, or to whomever. Additionally, CIA supports regional and national standardization, even if it's not initiated by CIA. And when there is a development for CAN-related standards, specification, technical reports, or recommendations. So whenever you see that something is ongoing, please inform us, and we will support them to make a proper documents then, so that everybody can implement this. And CIA is open to cooperate with other non-profit industrial consortia in the joint development and joint publication of CAN-related technical documents, including application notes and implementation guides. Just before we start going into the documents, just a hint. Joint documents need patience. So if you want to go fast, and that we want to go when we are developing standards and specification jointly, then go go together. If you want to have it very quick, then go do it by yourself, because this always needs some time. So how international standardization works. On the international level, we have two main standardization bodies, ISO and IEC. ISO develop things which is formally non-electrical, and the IEC is developing things which are related to electrical things. And we have regional or European level counterparts to ISO, this is CEN, and to IEC, this is CENELEC. And we have national standardization bodies, which participate in the international or regional standardization bodies. And we have, in addition, industrial consortia like CiA, REF, JASPER, SIE, etc. And they also contribute to the international standardization. But formally, for the international and regional standardization bodies, you need to be nominated by your national standardization body. Of course, in addition, we can influence, and we have cooperations with those national and international organizations by means of industrial consortia when we send our stuff to them and contribute. So there's a lot of editing rules and recommendations, and this is to make a high quality of documents available from the international and national standards. However, not everybody is respecting these rules, and some of the documents needs to be improved. And this is an ongoing business which we're doing every day. So there are some ideas avoid double specifications because they lead in long term to inconsistent documents and confuse the readers. Also avoid unclear requirements, recommendations, permissions, possibilities, and external constraints. And we have learned in the last 30 years a lot about this, and CiA is very committed to have high quality documents and supporting also the same quality on the international level. And of course, there is a part 2 of the ISO IEC directives, where are the drafting rules. This is a document of 93 pages, and this is boring to read them and to respect all these rules, but they are helpful to improve the quality of these documents. So, and I'm going to bore you even more with the following slides, full of numbers and abbreviations, but I hope still you can take some of the information and it's helpful for your daily work. So ISO is the home of the standards for the CAN protocol. And you know, ISO 11898-1 contains the CAN data link layer and the physical coding sublayers. We know that there are some issues in this document, which is published since 1 year, but this is just minor editorial improvements which we could fix in the next edition. The ISO 11898-2 document, which contained in the previous edition some not so nice things, or let's say some failures. And this is improved at the moment in publication. So that means we have passed all the votings, all the ballots, and you will have in a couple of weeks a very clean and high quality document available. Still, there might be some issues, but these are minor things. Then we have the ISO 11783 series, which is called also the ISO bus. And this is a J9039 based application profile for tractors and implements. This is partly in revision, and still there's a lot of things which are not so nice in this series, but we also step by step improve the quality of these documents. The ISO 11992-2 documents specifies the link between truck and trailer for braking and running gear. This is in revision because the previous edition was not implementable because of some missing information. Part 3 is in the moment under review, and there's an indication that there could be somebody request a revision, or it will be just republished as it is. For the, and this was already mentioned by, I think it's what Oscar, the ISO 15765-2, which is the ISO transport protocol, also known as TP. This is for diagnostic purposes, and this is in revision, and we will include in the new edition also the transport protocol for CAN-XL, because today it contains only the transport protocol for Classic CAN and for CAN-FD, but we need also to standardize CAN-XL the KNXL-based transport protocol to make diagnostic also for KNXL networks when they are introduced in the passenger cars. The same is for the in-vehicle network connections to diagnostic link connectors. This also needs to be revised because if you're running 20 megabit per second on the KNXL network, then you need also to have another connector, and this also needs to be improved. There's also the ISO 16844 series, which is also J1939 based for tachograph system. This is in revision, and I expect in this summer that we will finalize these documents. And also, Oscar has mentioned it already, ISO 16845-1 and -2, they are in revision. Part 2 is already in just these days. It was submitted for balloting. There are more CAN-related ISO standards. This is ISO 19642-12. These are the CAN, classic CAN and CAN-FD cables for passenger cars, but they need to be revised, and this document is open for comments in the moment. We also have the ISO 22166 series. This is an XML schema for CAN-based interfaces for service robot modules. This is still a development, and some parts are under revision. There's also a new document, ISO 23870. This describes a mapping and tunneling, and in the meantime, I know that the part number will be 31 for GigaNet for 1 gigabit Ethernet link. This is in development. We have still to do some basic work, I think. ISO 25200, this is for commercial vehicle body application network. So, for example, if you have a truck-mounted crane or you have something else, and this was formerly standardized in DIN 4630, and this is in development. And also this is, I think, close to be released by end of this year. Quite new is ISO 26343. This they can open profile for devices in emergency vehicles. In former time, this was called FireCAN, but it's not limited to firefighting trucks. It's also for ambulances and for other rescue vehicles. And this was before standardized in DIN 14700 from 2025. And this will be now internationally standardized in ISO. And we have the ISO 34730 series. This is a CAN-based, CAN-open subnetwork in smart greenhouses. This will be a generic specification for smart greenhouses, but there's also in the annex then a CAN-open based subnetwork described and how you can implement that. Already mentioned the CAN-related IEC standards. So there are several of them. The last one is the EMC evaluation for CAN transceiver, and this is in revision, and this covers high-speed transceivers, FD transceivers, SiC transceivers, and SiC XL transceivers. We also have a DC electric supply equipment for megawatt charging systems in development. This is IEC 61851-23-3. And we have that what is known as the CiA 402 profile, internationally standardized in IEC 61800-7-301 and 302. And this is also, I think it's pending since several years and there's no progress made, but still look to the CiA documents. And then you're on the safe side. If you want to have it internationally standardized, then you have still to wait until the committee is reopening the document and revising it. There are also some European standards. We have the CAN-open-based application profile for refuse collecting vehicles, also known as Clean Open. And this also needs to be revised. And this is published as EN 16815. And you have seen what Martin has mentioned, the EN 50325-5 CAN-open safety document. This also needs to be revised on request of Senelec because we are missing some things, the references are not correct, etc. There are also some German standards. DIN 14704. This is J9039 based firefighting specific parameters for the in-vehicle gateway units, and also this needs to be revised. I think there are some open issues, and we need to add some communication to telematic units in etc. But this will be, I think, not happen before the end of this century, the decade. DKE and VDE, they have an open-based interface for batteries and chargers used in forklifts. This is in preparation. I don't know in the moment the current status. We have lost communication to the original writers of this document. There are also CAN-related CiA specifications. CiA is an international organization in the United States for automotive and airborne applications. There's the well-known CiA J939 series, an application profile for on and off-road commercial vehicles. This is partly under revision. They have their own functional safety specifications, their own security specifications, and a lot of other things. This is similar to CAN Open, but a little bit different. And we have the CiA J2284 series. This is recommended practice for CAN CC and CAN FD connectable ECUs. And if they want one day also include CAN XL, then also these documents need to be revised. And there's another CiA activity regarding CAN FD interface for megawatt charging system for heavy-duty electric vehicles. And this is in development, but I think also this development is in the moment on hold. There are also IEEE specifications related to CAN. IEEE 1722. This is the mapping of CAN CC and CAN FD data frames into Ethernet frames, and this also needs to be revised or is in revision because also CAN XL should be included. The document is not easy to read, and there's a lot of terminology which contradicts to normal CAN terms which we are using, and it's hard to understand. We also try to use this for mapping CAN CC and CAN FD data frames for the isobus and for other things. But also this is still, when you are supporting higher layer protocols, you need additional specifications which might be not in the scope of IEEE. CAN-related VDMA specifications. As you might know, there is the VDMA, the German Association for Machine Builders, and they have developed the MIG 4.0 bus, this interface for the communication between machines, excavators and attachments, and this needs to be revised. It's also based on J939, and it is intended to submit this to ISO for international standardization in the ISO TC 127. In the moment, it is not clear what is the current status of this document because there is a lot of failures. We have submitted some comments, and in next month we will have discussion with them to improve that and to bring it to international standardization in ISO. There are also some CAN-related regulations, and you know that the UN ECE 13, this is the uniform provisions concerning the approval of vehicles of categories M, N, and O with regard to braking referencing. And they reference the ISO 11992 document, the part 1 for the physical layer and part 2 for the braking parameters and the parameter groups specified in this document. And there's also the implementation guide for this regulation, and they also reference then the same documents but with another date. And because some of these documents are not 100% backwards compatible, we have some issues with that. So this means we need to review also the regulations and to harmonize them. There's also another EU regulation regarding tachographs and for commercial vehicles. And there we are also going to harmonize this with the ISO 16844-7 document, which specifies the tachograph system parameters for diagnostic purposes. So as a summary, CiA is highly committed to support standardization. CiA staff participate as experts in many international, regional, and groups, including the German mirror committees. So this is in particular for the ISO TC 22 Subcommittee 31 Working Group 2, 3, and 4. This is for road vehicle data communication. For agriculture electronics in the Technical Committee 23, Subcommittee 19. For ISO TC 127, this is for the mainly for the construction machines, which also hosts the Ethernet, the 1 gigabit Ethernet link, where we have the tunneling of CAN frames. And we are participating in working group 6 of TC 299 for modular service robots. This mainly as Martin is doing. And we have the working group 2 in TC 347 for smart greenhouse automation. This includes also vertical farming, etc. And Rainer is participating in the IC TC9 working group 43. This is for train communication. And we have also a participation in the electrical drive profiles. But as I said, this is a little bit delayed in the moment. And we have the EMC evaluation of CAN transceivers, which we support from the National Mirror Committee. And we have also from Rainer supported the IEC Technical Committee 69 for public light electric vehicle charging. This is already covered, and we will see how we can make this more public available and more accepted in the markets. Refuse collecting is also another working group which we are active in, and of course, as I said, we have to update the clean open document because we have done some further developments not covered by the current EN specification. And CAN Open CC and CAN Open Safety. This is also in the Senelec Committee TC 65 CX. And for all the others, we are also there. CiA provides also liaison officers for some of the committees. So between the committees, and we also have liaisons with the standardization bodies. So CiA is accepted as a submitter of ideas to Subcommittee 31 of TC 22 and ISO TC 347. We also are partnering with a lot of non-profit associations. This includes IEF, AUTOSAR, Euromap, a European Space Agency, European Welding Association, JASPA, Japanese Association for In-Vehicle Networks, Open Alliance, International Association for Automotive Ethernet, Profibus International. So we have also a joint document there specified, and of course SAE, the SAE International for Truck and Bus Control Communication Networks Committee. And the SAE, this can't be done on the CiA level because there's an individual CiA staff membership necessary. I hope I have not give too much information to you and too many numbers, but we will provide these slides, and then you can look what is interesting for me, and then you can come with request to CiA and say, oh, I'm interested in that, how I can participate, how I can contribute. Okay, thank you for listening.